In this section, we're going to look at systems of equations that have three variables instead of two as in the previous section. So, we're going to solve a system of three equations that have three variables. And as a reminder, the solution should look like a three-tuple. In other words, x1 will be a number, x2 will be a number, and x3 will be a number. Now, here's an example of a system of three equations using the three variables x1, x2, and x3. And by the way, frequently you will see when you have three variables or three unknowns, frequently they'll use x, y, z. But you could imagine if you had an equation with, say, 30 variables in it, you wouldn't have enough letters. So frequently we'll just use x1, x2, and x3, and then it could go on all the way up to x30 or even more if we needed to. Okay, well first we want to realize that, well, let's review what our three legal row operations are. The operations that we can apply to these three rows, these three equations, that will not change the solution. But eventually we'll get it in a more simplified form, and then we'll find the solution. And the solution we find will end up being the solution to this system of equations. So the three row operations are, well, you can switch any two rows you want, which essentially means you can reorder these three rows in any order you want to. You could make the bottom one row 1, and the top one row 2, and the middle one row 3. The order doesn't matter. You are allowed to take any row and multiply it or divide it by any number other than 0. The other one is, and one we frequently use, is you're allowed to take any multiple of one of the rows. So take a row and multiply it by a number, and then add it to or subtract it from any other row. And you might notice that if we were to add rows 1 and 2 together to get a new equation, well, that wouldn't do much for us. That would give us two x1s. But if one of these x1s were negative, and we added the two equations together, a negative x1 and a positive x1, that would cancel out the x1s. They would be eliminated. That would greatly simplify things for us. So perhaps in the future, in a minute, we're going to take one of these rows and multiply it by -1. Okay, so for this example, let's eliminate one variable, and it doesn't matter if we choose x1, x2, or x3, but for this, just as a suggestion, we'll use x1. And we're going to remove x1 from two of the equations using these legal row operations. And that'll give us a system of two equations with two unknowns, and we'll solve it just like in the previous section. So as I alluded to a little bit earlier, if I want to eliminate the x1 here in equation number 2, it'd be nice if this row right above it had a negative x1 there. So I'm going to take row number 1, and I'm going to multiply it by -1. -1 times, maybe I'll call it equation 1 instead of row 1. And what does that give us? If we take this and multiply it by -1, we just have to change all of the signs. Negative x1 minus x2 minus x3 equals -5. Underneath that, I'm just going to write x2 with no change in it. Equation, row 2 or equation 2. That's x1 plus 2x2 plus 3x3 equals 10. Now, just simply by multiplying the first row by -1, we obtain two equations that have opposite coefficients on one of the variables. So we're going to add these two together, these two equations, and notice that this completely drops out because it's equal to 0. And then we have a 2x1 and a 2x2 and a negative x2. Well, that gives us a negative x2. And in this column we have a 3x3 and a negative x3. So that would be like a 2, positive 2x3. And then 10 and -5 gives us 5. And I made a mistake here. That's actually a positive x2. That was 2x2 minus x2. So here we have x2, I'll just scratch out that positive sign, x2 plus 2x3 is equal to 5. This is an equation that if you wanted to, you could call it equation number 4, if this one's 1, 2, and 3. It's a new equation that has only 2 variables in it. So now let's take a look at equation number 3. If I want to use equation number 1 to eliminate the x1 term from equation number 3, I would need for this coefficient to be a negative 2x1, right? So I'm going to write negative 2 times equation 2 would give us negative 2x1 plus minus 2x2 minus 2x3 equals negative 10. So negative 2x1 minus 2x2 minus 2x3 equals negative 10. All right, and then equation 3 we're going to leave alone, just like we did up here with equation 2. Equation 3 is simply 2x1 plus x2 plus x3 equals 6. And notice that we have the same situation as before. The variable x1 is going to vanish when we add these two equations together. So negative 2x2 plus 1x2 is negative x2. Negative 2x3 plus x3 is negative x3. When you add negative 10 and 6, you get negative 4. So here's a new equation that if we wanted to, we could call it equation number 5. So we have a new equation number 4, a new equation number 5 that both have the same 2 variables. So it's simply a system of 2 variables with 2 unknowns, and we'll solve these two just like we did in the previous section. So in part 2 of this problem, it says solve the 2 equations as in the previous section. That means this one and this one. So let's see what we've got. We've got, oh, this will be very simple. x2 plus 2x3 equals 5. And underneath it, I'll write negative x2 minus x3 equals negative 4. I don't have to do much work with this one. We were fortunate that the coefficients of the x2s are opposite signs, a 1 and a negative 1. So when we add these two together, we're going to get the situation again. x2 is going to cancel out to be 0. And we'll get 2x3 minus x3, which is 1x3, just x3, equals 5 and negative 4 is 1. So now we already know one of the 3 variables that we need to be solved. x3 is a 1. And we can now take the fact that x3 is a 1 and plug it into either one of these 2 equations to figure out what x2 is. I think it'll be really easy to plug it in right here. Since x3 is a 1, we have x2 plus 2. I'll go ahead and write x3. Now, 2 times 1. We know that that's 2 times 1 because x3 is 1. It's hard to see that 1 there. Equals 5. So that gives us x2 plus 2 equals 5. x2 equals, subtract 2 from both sides to get 3. So, just like in the previous section, we solved a system of 2 equations with 2 unknowns, and we got x3 equals 1 and x2 equals 3. Well, the third step is just to find out what the unknown variable is, the x1. So in step 3, it says plug the known values from part 2, the 2 with check marks by them, into the original equations to solve for the third variable, which is x1. So let's come way up here, and I'll just choose equation number 1. x1 plus x2 plus x3 is 5, and I'll rewrite it down here. x1 plus x2 plus x3 equals 5. And we know what x3 and x2 are, so that gives us x1 plus 3 plus 1 equals 5. And these two add up to 4, so x1 plus 4 equals 5. Subtract 4 from both sides to get x1 is equal to 1. Okay, so our final solution, written as a 3-tuple, would be x1, which is 1, x2, which is 3, x3, which is 1. Now, it would be wise to go plug in 1, 3, 1 into all three of the equations. It's easy to see that equation 1 is satisfied because 1 plus 3 plus 1 is 5. And let's jump down to the bottom one. I'll let you verify the second one. The bottom one, this would be a 2 times 1 plus 3 plus 1 equals 6. If that works, 2, 3, and 1 does add up to 6. And you'll find that it also works when you plug in the 1, 3, and 1 into equation number 2. So we're assured that we have the correct answer in 1, 3, 1.